Now, a brief summary of the whole ith trapezoid situation. Okay, the ith trapezoid, I stands for any number, in this case from 1 to 4. It could be the first, second, third, or fourth trapezoid. Whatever I is, that tells us which trapezoid it is. For example, if it's the third trapezoid, well, the third trapezoid is here, and y3 is here, y2 is here. So, if the number of the trapezoid is I and I is 3, then this has to be y sub 3, and in general, this is going to be y sub I. This is going to be y sub I minus 1, since the index here is 1 less than the index here. The width of the trapezoid is b minus a over 4, and it follows immediately that the slope of the trapezoid is rise divided by run. The rise is this minus this, y sub I minus y sub I minus 1. The run is the width b minus a over 4, so here's your slope. The area, well, we take the average of the altitudes for the usual reason, add this to this, divide by 2, that's here, and multiply that by the width here. Now, I've written it out a little more clearly over here. Okay, so the slope of the ith trapezoid then is y sub I minus y sub I minus 1 over the quantity b minus a over 4, the rise over the run equal to the width. And that can be rearranged to make it a simple fraction, putting this 4 in front here for the reasons that we've already seen. The area of the trapezoid is the average of the two altitudes. The altitudes are y sub I minus 1. We average those and multiply by the width of the interval. The accumulated area of the ith trapezoid is what? It's the accumulated area of the preceding trapezoid. If the index of the trapezoid is I, then the one before it has index I minus 1. So if I is 3, then I minus 1 is 2. So the accumulated area up through the third trapezoid is the accumulated area of the second trapezoid plus the area of the third, as advertised. And that occurs, that's going to be valid as long as I is bigger than 1. Now, if I happens to be equal to 1, well, the accumulated area of the first trapezoid is just the area through the first trapezoid. I should say the accumulated area through the first trapezoid is the accumulated area. It is just the area of the first trapezoid. Now, if we want to divide the interval instead of into 4 subintervals into some arbitrary number of subintervals, let n be the number of subintervals into which we want to divide it, what has to change here? Well, we're not going to have 4 of these. We're going to have n of them. So we're going to have to divide the distance from a to b, which is b minus a. Instead of dividing by 4, we're going to have to divide by n. Since we don't know what n is, and n might be quite a large number, since we don't know what n is, we're not actually going to be able to draw all of the intervals. So what do we do in that case? Well, in that case, I'm going to draw the graph from A to B, but I'm going to put a break in the middle. The break could be 1,000 miles long if we got a big number n. But we want to have a break there so we can draw the intervals of reasonable width and be able to label them. Okay, so and of course we're going to break the curve here, whatever the curve happens to be. So we got a big break in the middle. It could be as long as we want. Okay, but the interval is going to run from x equals a to x equals b, and the first value of x we're going to call x sub 0, so we can call the last value of x sub n. X sub n is going to be the last x value, and it's going to be equal to b. The first is going to be x0 equal to a. Then we have x1, x2, x3, so forth and so forth, maybe for billions of intervals, until we get to x sub n minus 2. So if n is a billion, x sub n minus 2 is 2 less than a billion, 999,999,998, if you want to say that. X sub n minus 1 is 1 less than a billion. That 8 becomes a 9. So we have a notation here that we can apply and give ourselves a calculation scheme, so that if we have a means of determining the value of y for every value of x, for example, a formula for the function or some other means of obtaining the value of y, we can proceed to label the altitudes with meaningful numbers. Now, the y0, y1, y2 aren't meaningful numbers, but they represent what will be meaningful numbers if we manage to complete our labeling or to complete our calculation scheme. If we have a billion intervals, I hope we have a computer that we can program to calculate the results. Okay? And then we're going to be able to calculate. Once we have the y values and we know the widths of the intervals, we're going to be able to easily calculate the slope, the area, and the accumulated area for each of the trapezoids. How do we do that? Well, here's trapezoid number I, and I'm sorry things got a little crowded there. I do that a lot. But the ith trapezoid is going to look a whole lot like it did before. The only difference is we're going to have b minus a divided by n, because in order to get the width of an interval, we have to divide this distance, which is b minus a, by the number of subdivisions. So each interval is going to have width b minus a over n, rather than the b minus a over 4 that we used previously. So if we use n equal subintervals from a to b, then there's the width, and that has to be the width of our typical ith interval. And I could be any number. That's going to be the width of every interval, no matter what I is. And of course, the altitudes, the right altitude is going to be y sub I. The index here is going to match the number of the trapezoid, and this is going to be y sub I minus 1. And then we, in a very straightforward manner, can simply write down what our slope is. The rise is y sub I minus y sub I minus 1, just like it was if we had 4 subintervals. The difference is the run, which is b minus a over n. And then, of course, we can proceed to simplify the fraction, put the n out in front, and then we have the yi minus 1 divided by b minus a. The area of the ith trapezoid is going to be the average of the two graph altitudes, y sub I minus 1 and y sub I, average them, multiplied by the width of the interval, b minus a over n. And the accumulated area is going to be exactly as it was previously, unless I is 1. For any I greater than 1, for any trapezoid greater than the first, we add its area to the accumulated area through the preceding to get the accumulated area through the present trapezoid. And the accumulated area of the first trapezoid is just equal to the area of the first, and there's our complete scheme.